The next chapter is called chemical kinetics. Kinetics is a term that refers to rates of reaction. So how fast is a reagent being consumed, or how fast is a product being formed. And the rates are like the speed of a car, meters per second. And in chemistry, we usually do molarity per second. So the rates are in molal per second. So how many moles are being consumed over time. And I'm only going to cover 3 sections, so it shouldn't take very long, and then you are ready for your first exam. So here we have a chemical reactions, and if you just look at the balanced stoichiometry here, we have 2 moles of hydrobromide forming 1 mole of hydrogen and 1 mole of bromine. So it is logical to assume that whatever the rate is, however fast it goes, that for every 2 moles of hydrogen bromide you produce 1 mole. So the disappearing rate is twice as fast as the appearing rate of, so for every 2 moles you get 1 mole of hydrogen. And so hydrogen gas and bromine gas. So the stoichiometry is important, and so when we express the rates, all we have to do is we have to take the, first of all, look at if it's a reagent or a product. And if it's a reagent, then you have a negative rate, and you take that factor, and so you divide it by 2 times the change in HBr, or the reactant here, over the change in time. So that would be the rate expressed in terms of the hydrogen bromide. If we want to do the same thing for the products, we can, and that's what this question is asking, except now we have 1 mole, so it's just the change in concentration of H2 over the change in time. And then the same thing is true for the change in concentration of bromide over the change in time. And so this would be number 1. So B, in the first 25 seconds of the reaction, the concentration of HBr drops from 0.6 molal to 0.512 molal. So this tells us the difference in concentration, final minus initial. This gives us the time, and it refers to HBr, so our rate is going to be calculated negative 1/2 times the change in concentration of HBr over the change in time, which is equal to negative 1/2, and then its final concentration, which is 0.512, just this number here, minus 0.600 m. I gotta have some units there, divided by the time, 25.0 seconds. So this is going to be, of course, a negative number, and so our rate will be positive 1.76 times 10 to the minus 3 molal per second. So this would be the overall rate. And the follow-up question here is, if the volume of the reaction vessel in part B is 1.5 liters, what amount of Br in moles forms during the first 15 seconds? So we know what the rate is. First of all, we're dealing with bromine, so let's write the rate expression for that. So it's the change in concentration of bromine divided by the change in time. And so we want to solve for this. We know what the rate is, we know what the change in time is, we're given that, and so we solve for delta Br. So delta Br2 is going to be equal to the rate, which is the same thing we just calculated, 1.76 times 10 to the minus 3 times time, which is 15.0 seconds. So we still keep our 3 significant figures, and so that's 0.0246 molal per second. That's for bromine, but they're asking for the number of moles of bromine, and they're giving us a volume, and we know that molarity is moles per liter, so we simply take the 0.0246 mol, which is moles per liter of bromine, and we multiply it by 1.5 liters, and so that gives us 0.0400 moles of bromine. Okay, this is actually pretty simple. So this is, as always, the worked out solution clean. Now we will work another one very similar, just to reinforce this concept. First, we're going to express the rate of the reaction in terms of all of the reagents and the products. We already know that the rate is going to be equal to negative 1/2 times the change in concentration of NO2 over the change of time, which is equal to, and then that's going to be positive, the change in concentration of N2 over the change in time, and then the same for O2, except here we have a stoichiometry of 2 moles, so this is 1/2. Okay. Follow-up question. In the first 15 seconds of the reaction, 0.015 moles of O2 is produced in a reaction vessel with a volume of 0.5 liters. What is the average rate of the reaction during this time interval? So we know that the rate is going to be equal to, this is O2, 1/2 the change of O2 over time. Now, we're not given molarity, we're given moles and volume, so we have to first calculate the molarity. That's pretty easy. 0.015 moles divided by 0.500 liters is going to be equal to 0.030 m. That is the change, or delta T. So what we want to do is we want to have, so it's 1/2 times 0.030 m divided by 15 seconds. And that gives me a rate of 0.020 mol per second. That is the overall rate of this reaction. So the follow-up question C on what we just calculated is to predict the rate change in concentration of NO2 during this time interval. Well, we already know what the rate of the reaction is. We just calculated that. It is 0.0020 m per second, and of course the rate is equal to minus 1/2 times the change of NO2 divided by delta T. So this is the rate, so we multiply this both sides by 2, and so the rate is simply, with respect to NO2, is simply twice that, so that's going to be equal to 0.0040 m per mol. Okay, last question. Here we have a data table. We measure the concentration of the reactant C4H8, which is decomposing to form 2 equivalents of C2H4, and so we have time versus concentration, and we can calculate any rate between any of the time intervals. And so it's asking us to do the rate between 0 and 10 seconds and 40 and 50 seconds. And so the rate law with respect to the reagent is equal to negative delta C4H8 divided by time. And so between 0 and 10 seconds, we can calculate that by the final concentration, which is 0.913 m minus 1.000 m over 10 seconds. So this is going from here to here. This is where my numbers are coming from. And that gives me a rate of 8.7 times 10 to the minus 3 mol per second. We do the exact same thing for between 40 and 50. The rate is going to be different, of course. I'm going to skip this part and go straight to between 50 and 40. So it is 0.63. I should put the negative there because it is a negative. And then of course this term gives you a negative, so that gives you a positive rate. So 0.0637 mol is final concentration. Initial concentration is 0.697 m. Also 10 seconds. And that gives me a rate of 6.0 times 10 to the minus 3 mol per second. So slightly lower than the rate earlier on. You know, as you deplete the reagent, the rate is going to slow, so that answer makes sense. And now I'm going to ask, what is the rate of formation of C2H4 between 20 seconds and 30 seconds? So now you got to be careful what it's asking for. It's asking for the rate of formation, which is of course related to the rate we can calculate. But so the rate is going to be equal to 1/2 times the change in concentration of the product C2H4 over time, which is related to what we can calculate, the negative change in concentration of the product C4H8. Sorry, it's the reagent over delta T that we can calculate. So between, let's go see here, 20 and 30 seconds. So we have 0.763 minus 0.835. That was the initial concentration. I'm leaving out the units. Shame on me. Divided by 10 seconds. That gives me a rate of 7.2 times 10 to the minus 3 mol per second. Now that is this rate here. Now if I wanted to solve for that, I have to multiply by 2. So this rate by 2 gives me 1.4 times 10 to the minus 3, sorry, it's 2 mol per second. So that is the rate of formation of the product. That is the end of the part that you're responsible for exam 1. Go work some active problems.